Yeah, so welcome back. Yeah, Friday to Wednesday, of course, we have a longish gap. All of you must have got the quiz marks. I think maybe even before the last class, I forgot. Yeah. Okay. So last time we did Laurent series expansion and also a few more applications of Riesz's theorem. I think we must have done fundamental theorem of algebra once again. We must have done open mapping theorem once again, this time using Riesz's theorem. I think I must have followed, yeah, I followed Conway's approach. Today we will come to Runge's theorem, and I won't finish it today. In lecture 1 itself, I named some famous theorems, and Runge's theorem was one of those. So we will start that. We will do the important part of it and continue in the next class. And maybe I will make one or two remarks before we go to the slides. Oh, by the way, I haven't opened my slides. One second, let me get my slides. Yeah. Yeah, we'll come to the slides soon. I have it on my desktop. One or two general points about Runge's theorem before we start. One is that some of you might remember, I might have said it very roughly. We will come to the precise statement on the slides. It's about approximating holomorphic functions by rational functions. We must have discussed this. One is interested in approximation by polynomials in general, but that's not always possible. It's not possible to approximate holomorphic functions by polynomials in a nice way, uniformly on compact sets. But by rational functions we can do, and we can prescribe by what kind of rational functions also. So that is Runge's theorem. We will come to the correct statement soon. So we will do, I hope to do two proofs. First we will do as in Rodin, and I must have said long back that it will use some functional analysis and measure theory. In fact, this was the reason why we stated one of those integrals being representable by power series in a more general measure theoretic context. I wanted to use it here. So we will do Rodin's proof anyway. I like that proof. So though it assumes something that we haven't done or some of you are not familiar with, I will state the results that we need to use and we will do it. And then maybe we will come back and do the proof as in Conway, which is more elementary. It doesn't assume anything, but it is again, I noticed only yesterday, though I had seen the proof in Conway long back. Conway mentions that proof is also somewhat new. It is from 1976. So maybe in another class we will do that proof if there is time. Okay, otherwise you can look at Conway for a more elementary proof. So let me share the screen and continue from there. Open share tray, screen. Yeah, one of you please confirm that the slides are visible.
Yeah, I can see.
Yes, sir.
Yeah, okay, good. So lecture 11, Runge's theorem is today's topic. So what we will do is, so Runge's theorem is for any open set, any holomorphic function on any open set. Set need not even be connected. But that we will not state today. We will do the crux of the matter, which is what is called Runge's theorem for a compact set. And then, you know, there's a standard way of deducing it for any open set. Here, you know, I mean, in that deduction, which we are not going to do today, that thing that I forwarded on WhatsApp, that result will be useful. In fact, when I was forwarding it, I was not sure where exactly we are going to use it, but it will be used. What is called compact exhaustion. Any open set can be written as a countable union of compact sets, chosen in such a way that it satisfies some nice properties. Okay, so today what we will do is Runge's theorem for compact sets. And yeah, so last time we covered the Laurent series expansion. And remember, while doing this Laurent series expansion, how did we do it? We took an annulus and we applied the Cauchy integral formula for the cycle which consists of the inner circle and the outer circle oriented appropriately. And therefore the function can be written as sum of two functions. One is one of the integrals, the other one is the other integrals. And we proved that both are holomorphic, where the outer one, where the circle was positively oriented, is holomorphic inside the disk 0 with that radius. The disk inside that outer circle, because that was positively oriented. The circle inside, because it was negatively oriented, the corresponding function was holomorphic away from 0, meaning in a neighborhood of infinity. So it was holomorphic for mod z greater than R1, where R1 is the radius. And we also showed that both these things are convergence is absolute and uniform on compact sets. I'm recalling that now because again today, both these aspects will come when we are proving Runge's theorem for compact sets. The same idea, so that idea is being used again and again and again. So the idea is something like 1 by z minus w. You can expand as a geometric series, and you can get. You can also show convergences uniform and absolute by the Weierstrass test. And this idea is going to be used again today. Okay, so we have seen it the very last time, Laurent series. And also we saw few applications of Riesz's theorem. We did FTA and OMT using Riesz's theorem. Today we will discuss Runge's theorem. So a few words, since it's an important result. The result is roughly about approximating holomorphic functions via rational functions. We will first do the proof in Rodin, which is using functional analysis and measure theory, which we will assume because proving all that, will take some time, but I will state it in a way that you can easily remember. Okay. So there's a more elementary proof. I did not know the history till yesterday, though I had looked at Conway before, but maybe I haven't looked at it so carefully. The proof is from 1976. I think the mathematician's name is Grabiner. Sandy Grabiner, S. Grabiner. We will, I might do it because that's more elementary, but later. Okay, so we'll do that in another class. As usual, discussion session is at the end where we can discuss. So first we will prove what is often called Runge's theorem for compact sets. Why do I say compact sets? Because I will be approximating a holomorphic function on an open set, but restricted to a compact set. On K, the compact set, I will try to approximate it by rational functions, and later we will say that on any open set we can do this. Okay, but that's not today. So general theorem for open sets will follow from this one. So this is the real crux of the matter, real thing that we should do. As mentioned earlier, today we will follow Rodin's approach, which is based on functional analysis and a theorem from measure theory. The two results that we need are, so many times, we may not fully know all the results that we are using, but still we should know clearly which result we are using, which one we actually know, which one we are assuming, etc. So remember, the results that we are going to use are, one is a statement, it doesn't have a name, but it's good to have names in order to remember. So the way to remember is there is this famous theorem, Hahn-Banach theorem in functional analysis. and it's an immediate corollary to the Hahn-Banach theorem. So what we are going to use is not the Hahn-Banach theorem, but a result which does not have a name. So I will still say it's Hahn-Banach theorem. It's an immediate corollary. So associating names as a way to remember things. So Hahn-Banach essentially. And the other one is RRT, Riesz representation theorem. So this is not the Riesz representation theorem for Hilbert spaces. This is the Riesz representation theorem in measure theory. I will state it in such a way that you can easily remember, though some of the words you may not know, but still the statement you can still remember. Okay. And these two we will use. We will also use Fubini's theorem, which we must have already used. Basically, you can change integrals under some nice conditions, and these nice conditions are always met in our cases. For example, you know, if it's if the integral is on a compact set, then changing the integral is justified by Fubini. So Fubini also we will use. There's one more ingredient which is related to Cauchy integral formula, which we will state at the right time. So these are the things that we need. So let's state these two results first. So first is Hahn-Banach theorem, actually a corollary. So these are about, you know, Banach spaces, functional analysis, norm-linear spaces. You don't need Banach, norm-linear spaces. So what is a norm-linear space? It's a vector space. You also have a notion of norm. So norm is some generalization of an absolute value. You will see all this well. So you have the notion of distance. Not only that it's a metric space. Metric space, you have notion of distance between 2 points, but you also have this distance between 0 and your vector. So it's a vector space, and you have the origin and distance between 0 and x, that is a norm x. So you know, you can abstractly say what a norm is. It satisfies triangle inequality, some other properties. It's like the absolute value. It has many properties like the absolute value. Okay, so a norm linear space is a vector space with a norm. This is the subject of functional analysis, and Hahn-Banach theorem says, and norm gives you a natural topology, right? Norm gives you a distance, norm of d of x comma y is norm of x minus y. So it's a metric space, therefore it's a topological space, and therefore you are not interested in, so you are interested in vector space, you are interested in linear functionals, and here you are interested in linear functionals, but here you are interested in continuous linear functionals, continuous with respect to this topology. So the question is, see, you know that in a vector space there are enough linear functionals. So the dual space is an interesting object to study. So here by the dual space we mean continuous linear functionals. So first of all, you need to know that there are plenty of, there's a rich supply of continuous linear functionals, and Hahn-Banach theorem guarantees that. So theorem states that on any non-linear space, if you take any continuous linear functional on any subspace, suppose X is your non-linear space and MB, the capital MB is subspace, no conditions, just any subspace. And suppose you know you have something in M star given. M star is continuous linear functionals on M. Suppose you have a continuous linear functional given on M, then the result says that it can be extended to a continuous linear functional on the whole of X. So on a subspace, you have, if you have a continuous linear functional, it can be extended to a continuous linear functional on X in a norm-preserving fashion. So on the dual space is also a Banach space. Dual space is also a norm-linear space. You can put the norm, what is called the operator norm, and therefore you can talk about, you have the norm of a linear functional. So this is a norm preserving extension. So the original linear functional in M star had a norm. The extended linear functional in X star has a norm, and these two norms are same. In that way you can extend. So any norm linear on any norm linear space, any continuous linear functional on any subspace has a norm preserving extension as a continuous linear functional to the whole space. This is what is called the Hahn-Banach theorem, very important result. And should I say a few more words about the statement, or is the statement clear? You have X, a norm linear space. You have a subspace M. you have a continuous linear functional given on M, you have given me, and I am asserting that there is a continuous linear functional on X whose restriction to M is the linear functional that you have given me. Then there's one more condition on norm preserving, which we don't really need. Is the statement clear? Okay, some of you might have already seen. Yeah. Go ahead.
No, I meant that it is clear, yes.
Yeah, okay, good. Yeah. Okay, so this is not what we need. What we need is a corollary to this. Just to keep in mind, because anyway you are going to see this in some other place, and always it's good to see once sometime back, then when you really see it, it's easier to absorb. So the import of Hahn-Banach theorem is that now you have got a rich supply of continuous linear functionals on X, because you can take, you can cook up subspaces. For example, you can cook up finite dimensional subspaces, right? You can take a finite, you can take, some basis vectors, you can take the linear span, you can cook up finite dimensional subspaces where it's easier to cook up linear functionals. All of them, afford extension as continuous linear functions. So you have a lot of continuous linear functionals on X star. So that's the import of the result on norm space. Note that there's no condition on the subspace. Whenever topology is there on many results, you may assume some subspace is closed or some such thing. There's nothing like that. Any arbitrary subspace. Okay, no condition on the subspace. Another thing to keep in mind is that typically, in many of our results, we will say in a unique fashion. There's no uniqueness here, and the proof is also not constructive. It's only, there's no it just says there exists, and the proof doesn't give any clue. The standard proof doesn't give, I think any proof doesn't give any clue as to how to get one such. Okay, so it need not be unique, and no condition on the subspace. All these are irrelevant for our purposes. The corollary that's of interest to us is about, you take a subspace M and you would like to understand the closure in terms of linear functionals. By linear functional, from now onwards, I mean continuous linear functional, which is also called bounded linear functionals. Because of the norm, a linear functional L is continuous, the same as saying it is bounded. What is bounded? A mod of L of x, right? L of x will be a complex number, so you take the absolute value that is less than or equal to some constant times the norm of x. Then it's called bounded. You can easily check that boundedness is same as continuity. Continuity implies boundedness, boundedness implies continuity. So we are interested in the closure in terms of continuous linear functionals. So the question is, if you take a point, when does it belong to M bar? So you take a point of x and you would like to ask when does it belong to M bar for a given M. So I didn't want to put x naught, I just wanted to say x, so I'll correct it. If x belongs to M bar, then of course x is, M bar is a closure of M. So x is a limit of xn's where xn's are in M. And suppose you take any L from x by M, the quotient space, and a continuous linear functional there. What this means is L is a continuous linear functional on X which vanishes on M, which is identically 0 on M, right? L is a continuous linear functional on X by M. So L is a functional on X by M means what? It's a functional on X which is 0, identically 0 on M. So suppose you have such a functional L and xn's are in M and L is 0 on M. So L of xn is 0, and by continuity L of x is 0. So if x is in M bar, for all these L's which are 0 on M, L of x is also 0 by the continuity of L, right? What we are going to say is that the converse is true. The converse is also true. So what we have shown is if x belongs to M bar and if L is 0, L is such that L is 0 on M, then L is 0 on x also. The converse is true, which means what? If there is a point where L is 0, for all those L which are identically 0 on M, then X belongs to M bar. Right? The converse of this statement. This is also true, and that is because of the Hahn-Banach theorem. So what we are saying is M bar, what we have shown here is M bar is contained in intersection of all these kernels, where L is on X by M. L is identically 0 on M. So L is on X by M. You take the kernel. What we have shown is M bar is contained in this. Hahn-Banach theorem says that, an application of Hahn-Banach theorem says that the other inclusion is true. This intersection of kernels is contained in M bar. So let's give a quick proof, because the proof is easy if you assume Hahn-Banach. So what we will show is intersection of these kernels is contained in M bar. Otherwise, we are going to show that if you take a point outside M bar, it is not in this intersection. If you take a point outside M bar, we have to show that it is not in this intersection. Not in this intersection means what? It's not in the kernel of L for one such L. So, given a point outside M bar, we have to cook up an L which is identically 0 on M, such that L of X is non-zero. Given X in M bar, you have to cook up an L which is 0 on M and L of X is non-zero. This is what we will do by Hahn-Banach theorem. So suppose X is outside M bar, and what does this mean? X is in M bar, meaning any neighborhood contains a point of M. So X is outside M bar, so there is a small neighborhood which will not contain any point of M. So there is a delta such that the distance between Y and X, distances with respect to the norm topology, so norm of Y minus X is bigger than delta for all Y in M. So now you consider the following subspace of X. M is already given to you. You attach X to M. X is outside M, M bar and outside M in particular. You consider the space generated by M and X, all linear combinations, right? The span by M and X. And on this space, I am going to define a linear functional. I'm going to define the linear functional L on this space. So anything on this space will look like Y plus a scalar times X, where Y is in M, and the value of that linear functional is that scalar lambda. This is well defined. Why is this well defined? This is well defined because, so I haven't written all the details. We are going. Yeah, there's nothing to check because on M, so define it like this. So any Y in M, there's nothing to check, right? There's no well defined. I'm taking a point in this span and I have defined it. So take a point, it will be of the form Y plus lambda X for some Y, and L of that is defined as lambda. So there's nothing to check here. This is defined, and this is clearly linear. You can check, take two things and check that it is. Yeah.
We'd have to check that if
your voice is breaking once again.
It is y1 plus lambda 1 and y2 plus lambda 1 is lambda 2. You check point this representation y plus lambda x is unique in the sense that there is only one lambda for which you can write it.
No, I don't. I also initially thought so, but I don't think we are doing any such thing. See, what is the space? It's a space generated by M and X, right? So anything here will look like Y plus lambda X for some Y and some lambda, no?
Yeah, but the same point could have two different lambda pairs. So we show that the lambdas will be the same. Since X is not in M, it will follow that there is a unique representation.
Yeah. So it's part of, for the definition itself, that also follows, because the way we have defined, no. So okay, once again, I'm getting confused. Once again, you're taking a point from this space, so that will look like Y plus lambda X for some Y in M and for some lambda scalar, right?
Yes.
Now, if you are saying that if this also can be written as Y1 plus lambda 1 X, right?
Yes.
Then I am saying that my definition is it is lambda 1.
Yeah.
Okay. So what we are showing is, so if Y plus lambda X is Y1 plus lambda lambda 1 x, right? Y plus lambda x is y1 plus lambda 1 x. So what are you getting? You are getting y minus y1 as lambda minus lambda 1 times x, right?
Yeah.
So what does that
Yes.
mean? Because it's x is outside M. So this means
Yes.
that is lambda 1. Yeah. Yeah. So yeah, you check that it's well defined. Okay. So this is a check because x is outside M, lambda is lambda 1. So this is well defined. I'm not writing all these details and I may not go back and write. We have spoken about it. This is clearly linear. You can check. What we need is this is also continuous. And that is also fine because you observe that if you take delta times mod lambda, that is less than or equal to mod lambda times norm of lambda inverse y plus x. This is because norm of y minus x is bigger than delta for all y in M. So lambda inverse y is also in M because y is in M. It's just a scalar multiple and M is a vector space. So this is in M and this is minus of minus x and minus x is in the space spanned by x. So this is of the form y minus delta y minus x. Therefore, that's bigger than delta. Mod lambda is mod lambda. So this is obvious. This is what is given to you. And now you can multiply this lambda inside. That's a property of the norm. So this is same as norm of y plus lambda x. So what is given to you is more. So you can observe that mod lambda is less than or equal to delta inverse norm of y plus lambda x. So which shows that this linear functional is bounded, right? Modulus of L of y plus lambda x, that is mod lambda, is less than or equal to a constant which is 1 by delta times norm of the point. So norm of L of v is less than or equal to a constant times norm of v. That is what is called bounded, which gives you continuity. Okay, so it's also continuous. Apply Hahn-Banach to this L on this space. So your subspace is the space generated by M and X, and you have constructed a linear functional which is continuous. Apply Hahn-Banach, you can extend this L to a linear functional on X, which is a continuous linear functional. And note that that functional restricted to the space M comma X is this linear functional, and therefore further restricted to M, it is 0. On M, this is 0, right? If this part is not there, then the answer is 0. So on M, this extended linear functional on X star is 0 on M. And what is the value at X? The value at X is 1. So apply Hahn-Banach to get an element of x star meaning continuous linear functionals on X, which is 0 on M and 1 on X. That's what we wanted to show, that if you take X outside M star, I can take a continuous linear functional on X, which is 0 on M and non-zero on X. This is what we wanted to show, and we are showing it as actually 1 on X, therefore it's non-zero. So this is shown. Okay, M bar is actually this. This is what we will use in the proof of Runge's theorem. That's one ingredient. Okay, I hope this is clear. And the other ingredient is Riesz representation theorem. We don't need the form that I am stating, but I thought, anyway in your measure theory class you might see this. So let me state it, and we will use a particular case. So let's state the general form. X is a locally compact Hausdorff space. I don't know your measure theory how generally you will do, but this is the general measure theoretic statement. You have a locally compact Hausdorff space, and you are interested in continuous functions on X which vanish at infinity. So on real line, for example, you can visualize vanish at infinity, meaning towards minus infinity and infinity it is tending to 0, right? Vanish at infinity. So in a general space, what is the meaning of this? If you give me an epsilon, I can choose a compact set like this interval in R, a compact interval. So a compact set depending on your epsilon, such that outside this compact set the function is less than the epsilon that you have given me, the absolute value of the function. Functions are complex valued, the absolute value of mod fx. Okay, so set of continuous functions which vanish at infinity. Vanishing at infinity means a function can be made arbitrarily small outside a compact set. You give me an epsilon, I will choose a compact set such that outside that the function is small. So it can be made arbitrarily small outside some compact subset. You will see in some other course that C0x is a completion of CCX. CCX is continuous functions with compact support. This C is for compact. Continuous functions with compact support. Here you put the sup norm. Norm of f is supremum of mod of fx. With respect to that, it's a metric space, and any metric space can be completed. And the C0x is nothing but the completion of this metric space with respect to the sup norm. This you will see later. We don't need all this for the following reason. But before that, let's state RRT. Keep in mind that even in calculus, you have seen integration as a nice thing. You know, it gives you linear functionals. So integration gives linear functionals on function spaces. If you have a space of functions, vector space of functions, then one obvious linear functional is, if you know how to integrate on those space, then integral of sum of integrals, etc., you are getting linear functionals. And most generally, you can integrate on measure spaces. And with respect to a given measure, you can integrate. So I must have recalled some words without getting into any detail. It's not possible to rigorously define all these things in 5-10 minutes. So I must have recalled some of these words, just quote unquote recalling. When we did that thing that if you take an integral on gamma dw by w minus z, that is representable by power series, we said that it can be done more generally on a measure space, right? We are going to use that today. So we integrate on measure spaces with respect to the given measure. So if mu is a nice measure, nice meaning, what is called a regular Borel measure. Let's not get into that. We don't need these details now. So if mu is a nice measure on x, then you can integrate with respect to that measure. Any f which is in C0x, you can integrate certainly. And f going to integral of f d mu is a continuous linear function on C0x. C0x is now a norm-linear space, and this is clearly a linear functional. It's also a continuous linear functional. Okay. This can be easily checked. This is not Riesz representation theorem. This is kind of easy to check. So given on C0x, you can write down an obvious linear functional, obvious continuous linear functional, which is just integrating f with respect to the measure mu. Integral over x f d mu. This is a continuous linear functional. Riesz representation theorem says that the converse is also true. Any continuous linear functional on C0x is given by a measure uniquely. So if you give me a continuous linear functional on C0x, then there is a unique, nice measure, a regular complex Borel measure, such that the linear functional L that you have given me, L of f is integral f d mu. Not just that, the norm of L is the norm of the measure. So on measures also you can introduce a norm. On this kind of nice measures you can introduce a norm. It's a norm linear space, and the norms are preserved. So it's a norm preserving isomorphism between two norm linear spaces, what is called an isometry. So there's an isometry between C0x star, the space of continuous linear functionals on C0x, and the other space, the other norm spaces, the nice measures, regular complex Borel measures on the space X. So there's a norm preserving isomorphism between these two. One way will give you this map. Given a mu, you can integrate with respect to that mu. That's a map, and that map is an isometry. That's Riesz representation theorem. It's given by a unique such measure. C0x star is the space of nice measures. This is also, the right hand side is also there's a natural norm, and that's a norm space, and this is an isometry. And nice meant some keywords here. So let's not get into that. This is the Riesz representation theorem. I said that we are not interested in the most general case because for us, X itself is going to be compact, not just some general locally compact space, but X is going to be compact. Therefore, C0x and CCX and all these things are just continuous functions on X. There's no vanishing it. Outside a compact set is backwards. There's nothing outside a compact set. So it is just CX. Okay. In that sense, it's easier. So all these are considered as norm spaces with respect to the sup norm. Norm of f, given a function in this space, norm of f is supremum over x in x modulus of f of x, sup norm. That's a norm, and with respect to that, this is a norm space. Okay, so functional analysis is coming into the picture because we are going to work with the norm space CK. K is a compact set. Okay. Let me also state what I, for just for recalling purposes, I call it, I mean, just for memorizing purpose, I call it compact CIF. There's no such terminology. I'm putting compact and CIF together because a compact set is there in the statement. So we are going to use the above two results, the corollary to Hahn-Banach and Riesz representation theorem and Fubini, of course, together with one more ingredient. This is the observation that given a compact subset of an open set, not assuming connectedness, the open set need not be connected, the compact set also need not be connected. In fact, not assuming connectedness gives you the power of Runge's theorem. So connectedness is never assumed in any of these results. So given a compact subset of an open set, say K contained in omega, we can choose a cycle gamma. Okay, this is the point of this observation. You can choose a cycle gamma. Where is the cycle outside K in omega? You can choose a cycle gamma in omega minus K such that you have the Cauchy integral formula with index 1. F of z is 1 by 2 pi I integral. This is your standard Cauchy integral formula. So standard Cauchy integral formula will say that Fz times the index is 1 by 2 pi I this whenever z is outside gamma star and whenever gamma is homologous to 0. Right? So we are saying that this is true for whenever f is holomorphic and whenever z is in K. Throughout K, this is true. So the point is to choose a cycle outside K. The claim is that you can choose a cycle outside K such that this is true with index 1. When z is in K, index is in 1. That is the point of the statement, right? Usual Cauchy integral formula, you are saying that for z in K, index is 1 and z outside omega, index is 0. It's homologous to 0 in omega. Such a cycle can be chosen. Such a cycle can be chosen. Okay. So we need to find gamma in omega minus K such that the index of z with respect to gamma is 1 whenever z is in K and it is 0 whenever z is outside omega. Then this result follows. This is the point. Then this follows by global Cauchy theorem. We will skip the proof because writing it down on Beamer is not so pleasant. But pictorially the proof is not difficult, so you can just work out the proof. We can discuss. Maybe I can draw some diagrams in the air by hand. Visualizing the picture is not difficult. It's one of the standard arguments which we would have done in calculus for Green's theorem and all that. Approximating using grids and right. In many proofs in complex analysis in 412, you would have seen this square grid arguments. The compact set can be covered with finitely many rectangular or even square grids, and standard argument integral on each of this grid will you will have cancellations because one edge and the opposite edge, etc. And using the square grids, you will conclude something for the indices, and wherever this edge and its opposite, all those things, deleting all those things just by going via the border, you will construct a polygonal path, and that polygonal path will do the job. That's essentially the idea. We can there's one or two subtleties we can discuss maybe during the discussion session. So one has to argue with appropriate square grids and also has to use the continuity of the index function. These are the two ingredients. It's easy. It's an easy proof. But pictorially it's very easy, and on Beamer it's slightly difficult to write it down. Therefore I'll skip the proof, but it's not difficult. So this is another ingredient. Okay. The point of this is that you can choose such a cycle outside K in omega using the compactness of K. Only then you can make sure that when you do the square grids, you can choose the grid size small enough so that all the grids are inside omega. When you cover K by grids, you can choose grids small enough so that all the grids are inside omega. So there you use the compactness of K. So we will assume this also. So let's skip the proof. We will discuss if you want during the break. Not the break, at the very end. Okay, let's come to the Runge's theorem. So statement, please pay attention. Important theorem, important statement. What is given to you is a compact set, nothing else. Okay. So statement is about approximating certain functions on compact set using rational functions. But it's a result in complex analysis. So complex function, holomorphic functions are yet to come. But what is given to you is just a compact set. Okay. And consider its complement not in the complex plane, but in the Riemann sphere. So what is the Riemann sphere? It is the complex plane together with the point infinity topologized appropriately, right? So for any complex point, its neighborhood is the usual neighborhood, usual open sets. Open disk is the usual open disk. And for the point at infinity, an open disk around that would mean uh, mod z bigger than some r, right? Away from 0 is a neighborhood of infinity. So a point of a d infinity r will be z such that mod z is bigger than r. Using this, you topologize, that is S2. And for all these results, it's S2 that is important. It is connectedness of S2 minus k, or the components of S2 minus k that will play a role. So consider S2 minus k. So you have a compact set in the plane given to you. You consider its complement in the extended complex plane, C union infinity, extended complex plane. Look at its connected components. So it may have several connected components. You look at that, and now you form a set. Okay, this set, I'm calling it capital A. This set A has exactly 1 point from each of these components. This is important. So you take 1 point from each component, and that is your set A. So you have this set A. What does it consist of? It consists of certain number of points, complex points, points from S2. It can be a complex number or it can be infinity. Infinity is not ruled out, and Rodin makes a remark, and it is true that most often the most interesting point to consider is infinity. Okay, but anyway, take a set of points from S2. What is the property of this set? From each component of S2 minus k, there is exactly 1 point in this A. There is a point in A from each component, and there is exactly 1 point in A from each component. Now suppose omega is an open set containing k. So what is given to you is a compact set, and suppose you consider an open set containing k and consider a holomorphic function on omega. It's a complex analysis result after all, so you have holomorphic functions on some open set, but it is a result for compact set. So what is given is a compact set, and with all these properties you have made some choices, and you have a open set containing this. So none of this is connected. Okay, k need not be connected, omega need not be connected. So consider a holomorphic function on omega. You're going to claim that f can be approximated by rational functions with some prescribed properties. So given epsilon, yeah.
Omega is in C, or are we considering it on the sphere?
Omega is an open set in C.
Okay.
Right, because we are doing but okay, I quickly made that remark, but let's see the proof also. That will make it very clear. Okay, so okay, let me put it this way, that omega contained in C is the crux of the matter. That's where it will be most interesting, because if you consider what is since the question has come, if you consider some subset in S2, then the only other point is infinity, and if you have a function holomorphic at infinity, what does that mean? So
F of 1 by Z is holomorphic at 0.
right, so what can you conclude about such functions?
If it's holomorphic on all of it, then I think it has to be constant.
Holomorphic on all of S2 has to be constant because S2 is compact, right? S2 is compact. So Lewis theorem. Yeah, let's come back to that. So omega is an open set containing K. Omega is an open set and C is what is of most interest to us, and we will see whether the other thing is part of it or ruled out when we see the proof. Okay, K is a plain compact set and omega is a plain open set right now containing K. Okay, so this can be approximated nicely. So given epsilon positive, there exists a rational function R. Now comes the interesting property. It's not just any rational function. These rational functions, so rational function meaning what? Polynomial by polynomial. So what it will have poles. What will be the poles? Poles will be exactly the zeros of the denominator, right? The poles can be prescribed. All of whose poles are in this set A that you have given me. So you are giving me A by picking one element from each component. You are giving me this A, and there is a rational function with this prescription that all its poles are from A, such that it is approximating f mod fz minus rz is strictly less than epsilon throughout z in K, for every z in K. So uniformly approximating on K. So the function, a holomorphic function on an open set containing K, can be uniformly approximated by rational functions with this nice extra condition that its poles are prescribed. It is from the set that you have given me. Okay, so this is Runge's theorem for compact sets. Okay, all right. So let's see the proof. We have time. Not so much time, but yeah, this will be enough because all the hard work is done. We have stated the results that we will use. So we will use the corollary to Hahn-Banach, we will use the Riesz representation theorem, we will use Fubini once, and we will use the compact CIF. Okay. So we are going to get into the slides, but remember the structure of the proof. Okay, maybe it's difficult to say without getting into it, but the point is we are going to use that on a disk. See, we are going to use integral dw by w minus z is representable by power series, and it's a standard technique which we have used many times. 1 by w minus z we will expand as a geometric series, and therefore on that disk 1 by w minus z can be written as a summation, a sum of functions f and w, where f and w, the summation is uniformly convergent, and f and w will be of the form something by something, where the denominator is w minus z power some n plus 1 summation over n, right? I mean the geometric series, whatever comes from the expansion. The point is those are what is coming in the summation, those are rational functions. And that's where rational functions and with some prescribed property, that's how we will set up the mechanism. And that's where we are going to use this thing. So, okay, so the condition on rational functions will be used there. So again, the crux of the matter is that as geometric series, when we expand, we are getting rational functions, and that's where it will come in the proof. Okay, let's see step by step. So the space that we are going to consider, this is a functional analytic input. It is CK with the sup norm. CK with the sup norm, and we are going to consider its subspace. What do we have to show? We have to show that anything here can be approximated by, we want to say that if you consider a holomorphic function on an open set containing this and restrict to this, then that can be approximated by rational functions, right? With this nice property. So we are going to consider the subspace consisting of those functions which can be approximated nicely, as we want in the theorem. So consider that subspace consisting of functions which can be approximated nicely by rational functions like that. So consisting of restrictions to K of all those rational functions, all whose poles are in A. So this is what we want to show. F is holomorphic on omega, then F belongs to this space. No, we don't want to show that F belongs to this space. We want to say that it can be approximated. So we want to show that F belongs to the closure of this space. So this space, let's call M. If you take F in H omega, omega containing K, we want to show that F belongs to M bar. And the approximation has to be uniform on compact sets, which means what is uniform approximation? Uniform approximation meaning approximation M bar in the uniform norm, in the sup norm. So we are considering with the sup norm. So we want to say that in the sup norm, when we take M bar, F belongs to M bar. That's the result. So Runge's theorem for compact set will we have to show that if omega contains K and if F is in H omega, then we need to show that F belongs to M bar. Is the statement clear? This is what we have to show. Because if F belongs to M bar, that means F can be approximated by these nice rational functions uniformly, because its bar is with respect to the sup norm. So if you take a holomorphic function on an open set containing K, then we want to show that F belongs to M bar. But what is M bar? We have stated this result that M bar is nothing but the intersection of kernel of L, where L is continuous linear functional on Ck which vanishes on M. Okay, so M bar is this is the first result that we know. And the second result that we know is L is a continuous linear functional on Ck. So we know how it looks like. Continuous linear functionals on any non-linear space. Continuous linear functionals on Ck on C0x where X is locally compact Hausdorff. So on any compact set K, and if you take Ck, continuous linear functionals are given by a measure on K, a nice measure on K, regular Borel measure on K, and integrating with respect to that. So we need to show that L on Ck, which is identically 0 on M, vanishing on M, this vanishes on F also, which vanishes on F restricted to K, right? F restricted to K is what we are going to consider, and any linear function on Ck vanishes on F restricted to K. But if you consider L in Ck star a continuous linear function on Ck, you know that it is given by a nice measure, such that L of F is integral F d mu on K. So therefore, what you have to show is if integral F d mu vanishes on M. What is M? M consists of rational functions, nice rational functions. Rational functions, all whose poles are in A. That is the space M. So if integral F d mu is 0, it vanishes on that space M. If integral F d mu is 0, for all those rational functions F, whose all poles are in A, then we need to show that integral F d mu is 0. So we have to show that suppose mu is such that integral R d mu is 0 for every rational function R with poles in A, then we have to show that integral F d mu is 0 where F is a holomorphic function on omega. Is the strategy clear? This would have shown that F belongs to M bar. Is the statement clear? If L is any linear functional on Ck, then it is given with respect to a mu. And if L is identically 0 on M, which means L of R is 0, that is integral R d mu is 0, then we have to show that L of F is 0, that is integral F d mu is 0. This is what we have to show. Now we are going to use this representable by power series argument on a general space. Okay, we are going to take, so on any measure space X, we had said that our proof goes through. So here the space is this compact set in C. So right, mu is a measure on K, and therefore integral d mu on K. So we are going to define this function h of z as integral d mu zeta by zeta minus z on K with respect to this measure. So you are giving me a linear functional that gives you this measure. With respect to that measure, you define this function. Where is this function defined? It is defined on S2 minus K. It is defined on any point outside outside K, right? Anything outside K, this makes sense. So this is defined in S2 minus K. So I'm considering this holomorphic function. I'm considering this function on S2 minus K, and the claim is that it is holomorphic on S2 minus K. Why is this holomorphic? That is the general argument that we have done long back using geometric series expansion idea, right? We showed that we proved it actually only for integral gamma dw by w minus z, and then we made this remark that any measure space the same argument goes through. So let's assume that we have to assume that general argument, and by that thing the standard argument using geometric series, this is holomorphic wherever it's defined. So that argument will show you that this is holomorphic on S2 minus K. Okay, so you are defining this H, and this is where, see, we have something given about rational functions, and rational functions are going to come here because this 1 by zeta minus z, when we expand, it will involve rational functions, and therefore, we are going to claim something about, we are going to claim something about these things, 1 by zeta minus z. That's where we will see rational functions. Okay. We are going to claim that H is identically 0 on S2 minus K. And how are we going to do this? So you choose a point in the set that is given to you. What is this set once again? This set consists of precisely one point from each of the component of S2 minus K. So take a point and take its component, the maximal connected set containing that point in S2 minus K, and we are going to show that H is identically 0 on V, on this component, and therefore H is identically 0 on S2 minus K, right? On any point on its component, we are going to show that H is identically 0. And what is the strategy? So if A is a complex number, A is in A, it could be infinity. I don't know which set you have given me. It might include infinity, it may not have infinity. But in particular, if A is a complex number, you take a small disk which is completely contained in V. Right? V is a component of A, and V is a component of containing this point A, and you can check that the components are automatically open because S2 minus K is open. So so V is open, therefore there's a small disk completely contained inside V, and you choose such a disk, and on this disk 1 by zeta minus z, right, 1 by zeta minus z is what we are interested in, and 1 by zeta minus z, you have the standard expansion as summation n going from 0 to infinity z minus a power n by zeta minus a power n plus 1. Right? This is a standard expansion which we have done long back, and also we recalled that during Lorentz series. And this is uniform for zeta in K, and this we are doing for a fixed z in DAR. So fix a z, and then this is uniform, convergence is uniform on zeta in K. Therefore, when you take integral of 1 by zeta minus z, integral can be interchanged and integral can be put here. Right? You are going to consider integral of this thing, z minus a power n by zeta minus a power n plus 1. Integration is with respect to d zeta. Right? Integration is with respect to d zeta. You are interested in d zeta by d mu zeta by zeta minus z. So integration is with respect to d mu zeta. So the point is, this is a rational function, right? This is a rational function in zeta, right? We are interested in showing what is given to you is integral r d mu is 0 for every rational function r. So r of zeta d mu zeta. So this is a rational function in zeta, and where is its pole? Its pole is, it has only one pole, and that pole is A. It comes with the order n plus 1. Just this much I am taking. Okay, it's a pole of order A, the pole at A of order n plus 1, but the poles are from A, and therefore integral of this with respect to d zeta is 0, and therefore this integral is 0. This integral is 0 because that's our assumption. Integral r d mu is 0 for whenever r has poles in A, and this is one such thing. Therefore this integral is 0, therefore this integral is 0 because of uniform convergence. You can interchange the sum and integral. If A is infinity, similar argument like in the negative part of the Laurent series expansion, 1 by zeta minus z, you can expand as minus summation zeta power n by z power n plus 1, and this has where does this as a function of zeta? It has a pole at infinity, right? 0 is a 0 of this, so it has a pole of order n at infinity, and therefore again the same thing. It is from your set A. Therefore this is a rational function R, right? It's a polynomial, so it's a polynomial with pole at infinity. So it's a rational function with pole at infinity, and therefore the integral is 0 again with the by the given condition for a fixed set. Okay, so the claim follows, H is identically 0 follows from our assumption and by the identity theorem. Why is that? What does our assumption say? Our assumption says that integral of this is 0 because integral r d mu is 0, and this is an example of one such r. So integral of r d mu is 0. Similarly, integral of r d mu is 0. This integral is 0, this integral is 0. By uniform convergence, this integral is 0, this integral is 0. But where? This integral is 0 on dAr, and this integral is 0 on d infinity r. And therefore by the identity theorem it is 0 on V, right? On a disk, and it has a limit point, it is 0, identically 0. Therefore it is identically 0 throughout V. Therefore H is 0 wherever it is defined. On all the components you have shown that it's identically 0. So the main step of the proof is this, that we define this function which we know is holomorphic on S2 minus k, and we have shown that this function is identically 0 on S2 minus k. What do we need to show? We need to show that integral f d mu is 0 if f is any holomorphic function on omega containing k. So that's what is remaining, and for that we will use Cauchy integral formula. So choose a gamma in omega minus k as in compact CIF, meaning gamma star is in omega minus k, and on k you have f zeta is given by 1 by 2 pi I integral fw by w minus zeta dw. This was a compact CIF whose proof is kept. Now we are interested in showing integral f d mu is 0, but what is integral f d mu? F of zeta is this. So this is integral of k d mu zeta f of zeta, but f of zeta is this. So just plug it in and apply Fubini and interchange the integral. See, gamma star is compact, k is also compact. So you are in the best situation where Fubini will automatically apply. You can interchange the integral and you will get 1 by 2 pi I integral gamma fw dw. What is remaining is integral over k d mu zeta by w minus zeta. You have just interchanged. But what is integral d mu zeta by w minus zeta? This is the function. This is the function which we have called hz. D mu by zeta minus z is hz on k. So this is h of w. D mu by z minus zeta is h of z. So this is h of w. So this is, sorry, d mu by zeta minus w is h of w. So this is minus of h of w. So with the minus sign, 1 by 2 pi I integral over gamma fw hw dw. But what did we prove about h? We proved that h is identically 0 on S2 minus k. And gamma has the property that gamma star is in omega minus k. Gamma star is outside k. And h is identically 0 on S2 minus k. On outside k, h is identically 0. And in particular, it is 0 on gamma star. So h is identically 0 on gamma star. Therefore, this integral is 0. So this is 0 because h is 0 on gamma star. as gamma star is contained in omega minus k. So this is the proof. So so whenever F is holomorphic on a compact set containing K is all that we use. So I remember coming back to your question, the proof doesn't say anything particular about the complex plane, right? This is the crux of the proof. This is for the first time F is playing a role, no? F hasn't come till here. Up to now we were arguing with K. F never came here. We define this H. And this has no F. F is coming only here in compact CIF. And compact CIF said that yeah. So let's go back to the slide on the compact CIF. So compact CIF said that if you have an open set containing K, then this is true. And its proof is just getting, so this is about this proof is Cauchy's theorem, and by constructing such a thing, yeah, so this is essentially Cauchy's theorem. So what was Cauchy's theorem once again? So where did we prove Cauchy's theorem? Cauchy's theorem said that, Cauchy's theorem meaning the global Cauchy integral formula. So the Cauchy integral formula said that you have such a thing whenever F is holomorphic on omega and gamma is homologous to 0. And what was omega in global Cauchy theorem? What was omega in global Cauchy theorem? In global Cauchy theorem, omega was a open set in the complex plane, right?
Yes.
Omega was a open set in the complex plane, and our proof was to define this omega 1, right? The proof that we gave, we extended the holomorphic function on omega to an entire function in C and applied Liouville. That was the proof, no? For a particular continuous function that we considered, using that we defined a holomorphic function, a new holomorphic function on omega, and extended it to an entire function in C. Therefore, there it was an open set in C. That's correct, no, Ariman?
Yeah.
Because if it was an open set including infinity, then extending it to C doesn't make sense. So it was an open set in C, and we are using this. So here also it's an open set in C. Nowhere else we used open set in C. In fact, I was arguing with S2 minus K. But at this particular step, so up to now I haven't used that, but at this particular step I am using that. So I think it's an open set in C. Okay. It's an open set in C, and that's where I am using this, because this uses global Cauchy's theorem, and that was for an open set in C. So okay, so maybe there's an important point. It's a good question that you have asked. See, it's also I must stress you, others also I encourage. Aryaman is asking a lot of nice questions. Onkar is also asking once in a while good questions, mostly in the discussion session, but ask in the regular recording session, I would say. See, after all, thanks to it's not a great thing that we are suffering because of corona, but anyway, one thing that has happened is I am making these slides instead of just giving spontaneous lectures in the classroom where I make even more mistakes than this. This at least one set of slides I am typing, so there's a little bit more care, but still, as you see, when I put the slides on Moodle, there are certain things that I strike out thanks to your comments. So mistakes are getting corrected. But one advantage, so whenever feel free to ask, you ask either during the video recorded lectures, which we are putting on YouTube actually, or during our private recording sessions. But one advantage of asking in the so-called YouTube lectures is, suppose, these are advanced topics, not many people are interested, but suppose, in the next many years, there is one student somewhere sitting in the world, somewhere, who happens to look at these lectures seriously. Suppose, it may be a non-empty set, no, outside this class, in time and in space, if you take, they could be, one student sometime, at some point in time, somewhere, who looks at these lectures. And lectures may have mistakes, but, if there is a question, that particular student also gets benefited, right? So it's good to ask questions. It's good that, my mistakes are getting corrected during the recorded part. So there's an advantage of mistakes are natural. Natural certainly for me, but good that, you ask during this part. But if you're not comfortable asking during this part, then of course, feel free to ask in the other part. But there's one advantage here, because these are recorded, and someone else also might benefit from our discussions. Might. Okay, so let me say that this is for an open set, and I will think about it once again after this class. It's always easier to think when you are alone, not in front of all of you, and then I might add a remark in the slide. Okay. So this part of the proof is clear, no? This is just change of integral and what we have used. Yeah, so the proof is slightly conceptually complicated, but simple, I would say, because there's a structure. And one advantage of using advanced mathematics is it gives a structure, and the proof is easier to recall once you assume those results. But let me, if there is time, I will also do the proof in Conway, which I realized is a proof from 1976. And I downloaded that paper. Of course, I will follow Conway only, but I downloaded that paper also just to, see the introductory remarks in that paper. And this is that paper. You can see whatever I share, right? You can see this, no? Ariman, can you see this paper?
Yes.
Yeah.
Yes.
Called
Yeah.
Short of Runge's Theorem by Sandy Grabiner. I forgot to check who Sandy Grabiner is. We will do it soon. So it's December 1976, and it came in American Mathematical Monthly. It's an expository paper, and you see the paper. Paper starts here, and paper ends here, and it has all these references. Rudin is there, Conway is there. So this is Conway 1973, and the Conway that we must be looking at must be later, because this proof is the proof in Conway now. So he is from a college, Pomona College. Oh, by the way, I think this is a very famous college. It's very well known for their teaching reputation, I think. And it's quite simple. And what is proved is for compact sets. Is the font big enough for you to read? Sorry, how do I get this part? With this kind of font, can you read this? Okay, let me try to read. I find it.
I can zoom in so I can read.
When I zoom, I can also zoom, but when I zoom, it's going outside my screen. I'm not able to. Okay. So I can also zoom. So yeah. See, the introduction says K is a compact. So he is also going to do. Okay. By the way, Sandy Grabiner. I don't know the. Yeah, whatever. I don't have so much time, so sorry. Yeah, I can also zoom, and I am here. So makes a remark here that we are going to do Runge's theorem for compact sets. This is the theorem that we just proved, because other versions of Runge's theorem for approximation of open sets. This is the most general Runge's theorem, which we are going to do in the next lecture. But these are simple topological consequences of Runge's theorem on compact sets. So the crux is to prove Runge's theorem on compact sets, which we have done. And others, using the compact exhaustion, etc., it will be elementary topology only. And then, the historical remarks, the importance of Runge's theorem is very important. So despite the importance in both classical and functional analysis, the usual proofs have drawbacks. I don't call it drawbacks, but whatever. So let me put quote unquote here. Drawbacks which often cause it to be omitted from elementary courses. The classical, so this is an argument that I don't know, this must have been the very original proof. Translation of Paul's argument is somewhat tedious. The elegant abstract proof, that what we have done is one such proof. Elegant abstract proofs are based on the observation that BS is a Banach space. Norm-linear space is enough. What is a Banach space? It is a complete norm-linear space. It's a norm-linear space which is also complete. Okay, and uses Hahn-Banach theorem and also Riesz representation theorem. So I think 6 is Runge. So that's what we have done. The proof we give is elementary. It doesn't use any complicated thing, but this is the important sentence for me, which Conway may or may not have. It is motivated by the fact that the space that we are considering, what we have written CK. No, is it CK? This BS may not be CK. Okay, so I haven't read this paper yet. I will read it just before the next class. BS be the collection of all functions with the uniform limits on K of sequence. Yeah, BS is what we call M. BS is what we call M. So M is a subspace of CK. So what he is calling BS is what we call M, and we showed that F is an M bar. So it is motivated the fact that M is a Banach algebra. So see, whenever you simplify a abstract proof, there's an abstract idea that is required. The proof that he is writing down is more elementary, but it requires an abstract idea, which is that M is a subspace of a Banach space, a subspace of a nonlinear space. Therefore, that's also a nonlinear space. It happens to be a Banach space. M bar, okay, M bar, not M, but M bar. So it's M bar is by definition closed. So it's a closed subspace of a Banach space. Therefore, that's also a Banach space. So M bar is a Banach space, but it is also a Banach algebra. So that's extra structure. There's a multiplication which has some compatibility with the norm. We are not going to use the word Banach algebra in this proof. Conway, I don't think uses that word Banach algebra. So it appears elementary, but it is motivated by this observation, and that observation can be written in terms of elementary things, and that's how the proof will go. Let's do this proof. It's interesting. Okay, so we will do this proof. So it's closed under uniform limits. Runge's theorem is an immediate consequence. So let's do this. Okay. So Conway 73. Our edition of Conway must be after this, because this is the proof that is given. So how do I put this? One more thing which I thought I should check, but I did not check, is who is Sandy Grabiner? I did go to MathSigner to get that paper, but I did not check who this is. So this is Sandy Grabiner. Okay. No, I got confused. See, I am not very comfortable with all this first names abroad, and I got confused with the first name Sandy, whether it is gender. So okay, so Judith is certainly feminine. Judith Grabiner is a historian of mathematics, and her husband Sandy Grabiner. I guess it's the same Sandy Grabiner. Yeah, Sandy Grabiner from Pomona College, we said, yeah. Yeah, Sandy Grabiner. So this is the mathematician. And he does functional analysis. His expertise is Banach algebras. So it's natural that he thought about this particular proof. And the proof is from 1976. Oh, he must have been quite young at that time. He joined Pomona College in 74. Okay, good. Okay, so some advantages of online classes. I can do, whatever I want to check in front of you. Okay, I think we have taken a lot of time. Let me stop this recording and start the next recording.